Titan is lying to us. From a distance, it looks like home. It has rivers, lakes, coastlines, rain, clouds, seasons, and a thick atmosphere that wraps around it like a blanket. If you squinted at the right photograph, you could mistake it for Earth. NASA scientists have said exactly that. They've stood in mission briefing rooms, looked at radar maps returned by the Cassini spacecraft, and found themselves reaching for words like drainage basin and shoreline and river channel, the vocabulary of Earth, applied to a moon orbiting a gas giant more than 1 billion kilometers from the sun. And that resemblance is the trap. Because Titan isn't Earth. Titan is a freezing, toxic mockery of Earth, a world that borrowed our planet's face and filled it with poison. It is the solar system's most elaborate bait and switch, a world that offers you the grammar of home and hides something fundamentally, irreversibly alien in every single sentence. It orbits Saturn at roughly 1.2 billion kilometers from the sun, 10 times farther than Earth. Let that distance breathe for a moment. The light that left the sun 8 minutes ago to reach your eyes took more than 1 hour and 20 minutes to reach Titan. By the time it arrives, it has spread and thinned and weakened until the sun itself is barely more than a bright star in a permanently hazy orange sky. Not a sun you warm your face under, a sun you have to squint to find. At that distance, temperatures at the surface hover around -179 degrees Celsius. That is not just cold. That is cold enough to make steel brittle, cold enough to crack certain metals like glass, cold enough to freeze carbon dioxide solid. And carbon dioxide is what we exhale as waste gas. At -179 degrees, methane, the gas you'd smell near a leaking stove burner, the gas that burns in your kitchen, becomes a liquid. And that liquid methane is what fills Titan's lakes and rivers, not water, methane. The rivers on Titan are not blue. They are dark and hydrocarbon thick, more like oil than anything you have ever swum in, and they empty into seas so large they have their own waves. When the Cassini spacecraft arrived at the Saturn system in 2004, after a 7-year journey from Earth, it carried a passenger. A small atmospheric probe called Huygens, built by the European Space Agency, bolted to Cassini's side and dormant for most of the journey. On January 14, 2005, Huygens detached from Cassini and fell toward Titan's surface. It took 2.5 hours to descend through the atmosphere. 2.5 hours of data streaming back through space, painting a portrait of a world nobody had ever touched. What it saw on the way down changed how we think about moons, about planets, about what it actually means for a world to look familiar. The atmosphere hit first, and it hit like a wall. Titan's atmosphere is roughly 1.5 times thicker than Earth's, the only moon in the entire solar system with a substantial atmosphere at all. Mercury has almost nothing. Mars has a thin whisper of carbon dioxide. Our own moon has essentially zero. But Titan has a real sky, a sky with weather and wind and chemistry churning in the upper layers. It is mostly nitrogen, around 95% nitrogen in fact, just like Earth's atmosphere. On paper, that sounds almost comforting. Nitrogen is benign. It is the gas that makes up the bulk of every breath you take. On Titan, that statistic means nothing at all. The remaining 5% is a cocktail of methane and hydrogen, laced with trace organic compounds, complex molecular chains that react with the weak ultraviolet light, filtering down from the distant sun to produce a permanent, planet-wide orange photochemical smog. That smog doesn't break up. It doesn't clear on a sunny afternoon. It sits there, thickening in layers, scattering light in every direction. Sunlight barely reaches the surface. If you were standing on Titan at local noon, beneath the point in the sky where the sun hangs, the light would be roughly 1,000 times dimmer than a clear sunny day on Earth. Not twilight, not deep overcast. Something closer to the light you'd find indoors, far from a window. You would see your hands in front of you. You would not see the horizon clearly. You would not see blue sky, or any sky at all, only an orange-brown ceiling stretching from one horizon to the other. And it would never change. Because the smog is everywhere, all the time, in every direction, at every altitude between you and space. Huygens recorded the sound of its descent. Wind, actual wind buffeting the probe as it dropped through layer after layer of haze, turbulence pushing against the parachute, the data clearly showing oscillations and gusts at different altitudes. Titan has weather, not metaphorical weather, not a theoretical hydrological cycle scribbled in a planetary scientist's notebook. Real weather, real atmospheric dynamics, a system that has been running continuously, recycling methane through the same evaporation condensation, precipitation loop for billions of years. Methane evaporates from the surface lakes and seas, rises through the lower atmosphere, cools and condenses into clouds at altitude, those distinctive bright smudges that Cassini's cameras occasionally caught forming over the poles, and eventually falls back down as rain. The rain carves channels into the ground. The channels feed rivers. The rivers carry material downstream and empty into lakes and seas. Every one of those words, evaporation, condensation, precipitation, erosion, drainage, applies to both Earth and Titan. The machinery is exactly the same. The fluid is methane instead of water. And that substitution changes everything in ways that are not immediately obvious and deeply, deeply dangerous. Ligeia Mare, one of the largest seas near Titan's North Pole, covers roughly 130,000 square kilometers, bigger than Lake Superior, the largest of the Great Lakes. Krakenmeer, the largest confirmed body of liquid on Titan, stretches to somewhere around 400,000 square kilometers, comparable in area to the Caspian Sea on Earth. From orbit, radar maps of these features look like coastal surveys from Norway or British Columbia. Inlets, peninsulas, islands, drainage basins, river deltas. The coastlines of Titan read like coastlines of Earth because the same physical processes, liquid flowing downhill, eroding banks, depositing sediment at mouths, shaped them both. The agency is the same. The chemistry is alien. And the difference between those two things is the difference between a world you could visit and a world that would kill you in ways you hadn't anticipated. It looks like a destination. It is a series of traps arranged to resemble one. Methane rain on Titan doesn't fall the way rain falls here, and that is one of those details that sounds like trivia until you understand what it means in practice. Gravity on Titan is only about 13.8% of Earth's, about 1/7 of what you feel standing on this planet right now. The atmosphere is thick, nearly 4.5 times as dense as Earth's at sea level. Those two facts together mean that raindrops on Titan would be large, perhaps a centimeter across, and they would fall slowly. Not gently, but slowly. Drifting down through thick air at reduced gravity, taking minutes to cover the distance that rain covers in seconds on Earth. If you've ever watched rain fall in a slowed-down video and found it almost hypnotic, Titan's rain would look something like that. Vast, lazy drops moving through orange haze, almost reluctant to reach the ground. If one of those drops landed on your suit, it would not splash the way water splashes. It would spread, slow and oily and cold. It would wick into any material with the wrong surface properties, and it would begin, immediately, to do chemistry with whatever it touched. Methane is not just cold liquid. Methane is a solvent. It dissolves certain plastics and rubbers at cryogenic temperatures. Seal compounds that work fine in water, and that have been tested extensively in water, in cold water, in salt water, in every aqueous environment engineers can conceive of, fail catastrophically in liquid methane at -179 degrees. The material science required to build a suit that remains airtight, flexible, and chemically resistant in those conditions is not solved. It is a research problem that nobody has had to solve before, because nobody has been to Titan before. If your pressure suit used the wrong compound in its joints or gaskets, a detail nobody would catch without the right kind of targeted laboratory testing that is expensive and slow and requires a test facility that essentially doesn't exist yet. Titan's rain wouldn't just soak you. It would begin to compromise the integrity of the only barrier between you and an atmosphere that cannot be breathed, in temperatures that cannot be survived without constant thermal management, at pressures that require the suit to be a working mechanical system every single moment you are inside it. A single compromised seal, a single material failure at a joint. That is not a doomsday scenario requiring extraordinary bad luck. That is a foreseeable failure mode of a technology that has not yet been developed. And on Titan, there is no emergency return vehicle sitting nearby. There is no rescue option within any reasonable time frame. There is only you, the compromised seal, and a moon that will not negotiate. The ground that Huygens landed on was another surprise, and another reminder that Titan hands you the expected shape and fills it with something wrong. The probe hit the surface and didn't bounce. It didn't skid. It sank slightly, a few millimeters, the data suggested, and then settled. The penetrometer on Huygens read a surface behavior consistent with something like wet sand or well-compacted clay, a thin, hard crust over a softer substrate below. Except the moisture in that substrate wasn't water. It was liquid hydrocarbons, trapped methane and ethane slowly percolating through sediment layers that had been accumulating for millions of years. Titan's ground is wet. The wetness is not water. Before the batteries died, the camera on Huygens captured one image from the surface. Just one. A flat plain scattered with rounded pebbles and cobbles of varying sizes. They looked exactly like river rocks on Earth, smooth, rounded, clearly shaped by long exposure to flowing liquid. The erosion patterns were identical. An imaging scientist on the team later said it could have been a dry riverbed in Arizona. A familiar, unremarkable sight that could have been anywhere. It was nowhere on Earth. Those pebbles were not made of granite or sandstone or basalt. They were made of water ice, frozen harder than rock at those temperatures, and they had been shaped not by rivers of water, but by rivers of liquid methane that had long since dried up, shifted course, or retreated with seasonal changes to lower elevations. The resemblance was perfect. The reality was completely different. That is Titan's signature move, and it plays it everywhere you look. Consider the dunes. Cassini's radar instruments, during repeated flybys over more than a decade, found vast fields of sand dunes near Titan's equator, long parallel ridges stretching for hundreds of kilometers across the landscape, covering an area roughly equivalent to the continental United States east of the Mississippi River. They look almost identical to the linear dunes you'd find in the Sahara Desert or the Namib in southwestern Africa. Same scale, same spacing, same sinuous, wind-sculpted shapes. The Fezzan region of Libya, the Namibian Dune Sea, the Great Erg of Algeria, all of these would be visually recognizable terrain patterns on Titan. The visual comparison is striking enough that geologists trained on Earth can read the terrain instinctively, recognize the patterns, feel the familiar logic of aeolian sediment transport. Except the sand is not silica, not quartz, not any mineral you'd find on a beach. The particles are made of tholins, complex organic molecules that form when ultraviolet light from the distant sun interacts with methane and nitrogen in Titan's upper atmosphere. These molecules are large, dark, and slightly sticky. They clump together in the upper atmosphere, grow heavy, and drift slowly downward over millions of years, accumulating on the surface in layers of dark, organic sediment. The ground beneath the dunes is not rock covered by sand. It is rock buried under chemistry. Chemistry that would be toxic to breathe. Toxic to touch, toxic to eat, utterly unlike anything on any beach or any dune field or any desert on Earth. Titan's equatorial dune regions are essentially enormous chemical landfills shaped by wind into structures that look like the most beautiful deserts on Earth. There is a detail about those dunes that doesn't receive enough attention, a detail that reveals something deeply strange about Titan's atmospheric dynamics. The dunes move in the wrong direction. Titan's prevailing equatorial winds blow from east to west, which is consistent with its slow rotation. Titan takes about 16 Earth days to complete one rotation, and the general atmospheric circulation pattern reflects that slow spin. The dunes, however, point west to east. For years after the discovery, this made no sense to the planetary scientists examining the data. The leading explanation developed over time is that Titan occasionally experiences powerful equatorial storms, brief but violent methane downpours that generate intense surface winds blowing in the opposite direction from the normal prevailing breeze. These rare storms are strong enough to overwhelm the everyday wind entirely and shove the dune sand the other way, leaving a permanent record in the landscape of violence that happens only occasionally, but with enough force to override years of quiet, steady drift. Think of it this way. The ordinary weather builds the dunes slowly, grain by grain, in one direction, over months and years. Then a storm hits, and in a matter of hours, the whole pattern pivots. The dunes record the storm in their orientation for centuries afterward. Titan's deserts are not just alien in composition. They are sculpted by tantrums, by episodes of atmospheric fury that leave no other visible trace, no craters, no flood damage, no scour marks, just dunes pointing the wrong way, in permanent, silent testament to weather events that may not have occurred within human memory of any civilization on Earth. It is a world where the ordinary and the violent have been collaborating on the same canvas for billions of years, and the result is terrain that looks familiar and is built from chaos. And beneath all of it, something even stranger, something that required years of painstaking measurement and complex orbital mechanics to detect at all. During Cassini's repeated flybys of Titan between 2006 and 2012, scientists measured tiny variations in the moon's gravitational field, minute perturbations in the spacecraft's trajectory, fractions of a millimeter per second change in velocity that revealed the internal distribution of mass. The data told a story that nobody had fully anticipated in that form. Titan's surface doesn't sit on solid rock. It sits on ice. A thick shell of water ice, estimated at somewhere between 50 and 100 kilometers deep, wrapping the entire moon. And below that shell, almost certainly, there is a global ocean of liquid water, perhaps mixed with ammonia, which would act as antifreeze and keep it liquid at temperatures well below 0 Celsius by lowering the freezing point. A hidden ocean, completely enclosed, inaccessible from the surface by any current or foreseeable technology, unknown to anyone until a spacecraft detected gravitational anomalies from hundreds of kilometers above. Titan has two faces. The one on top is a frozen methane world dressed up in Earth's clothing. The one below is a hidden water world that we cannot see, cannot touch, and can barely detect with our best instruments from a great distance. And that second world raises questions that keep astrobiologists awake long after their colleagues have gone to bed and stopped thinking about their data for the night. If there is liquid water beneath that ice shell, and if the base of the ocean is in contact with Titan's rocky core, then there is a genuine possibility of hydrothermal activity at the ocean floor. Hot water reacting with rock, mineral-laden fluid rising through fissures, cooling and depositing chemical gradients as it goes. This is not speculation about exotic or unprecedented conditions. This is the same recipe that powers the ecosystems around hydrothermal vents at the bottom of Earth's oceans. Places like the Lost City hydrothermal field in the mid-Atlantic, and the black smoker systems along the mid-ocean ridge network, and the axial seamount off the coast of the Pacific Northwest. In these places on Earth, entire communities of organisms live in permanent darkness, under crushing pressure, without any dependence on sunlight at all. They run on chemosynthesis instead of photosynthesis. They are fed by geology rather than by stars. Tube worms 3 meters long. Blind shrimp clustering around vents. Microbial mats covering square kilometers of seafloor. Life without the sun, drawing energy from the interior of the planet, thriving in conditions that biologists once declared would be uninhabitable. If Titan's subsurface ocean has that same geological activity at its floor, it might have the same recipe. Not life as we know it at Earth's surface, not life that needs light or air or soil, but life as we know it at Earth's deepest, darkest, most extreme environments, life that borrowed nothing from the sun. And that possibility sits there, suspended in liquid, 1,000 kilometers beneath Titan's methane lakes, in permanent darkness, under crushing pressure, in an ocean nobody can currently reach, possibly doing chemistry that would look familiar if we could only get an instrument down there to measure it. But the surface has its own strange candidacy for biology. And this is where Titan moves from merely extraordinary to genuinely unsettling as a scientific object. In 2015, a team of researchers at Cornell University published a theoretical study asking a pointed question. What would a cell membrane look like if it had to function in liquid methane instead of liquid water? On Earth, our cells use lipid bilayers, thin sheets of fatty molecules that form a barrier by orienting themselves in water, hydrophobic tails pointing inward away from water, hydrophilic heads pointing outward into it. The whole architecture depends on water's properties. That chemistry doesn't work in methane. The temperatures are too low. The molecular behavior is completely different. The intermolecular forces that cause lipids to self-assemble in water don't operate the same way in a cryogenic hydrocarbon solvent. The Cornell team proposed a theoretical membrane they called an azotosome, built from nitrogen-containing organic molecules, specifically acrylonitrile, which is present in Titan's atmosphere in measurable quantities, that could, in principle, form stable, flexible, self-sealing structures in liquid methane at Titan's surface temperatures. The stability of these theoretical structures in methane was comparable to the stability of lipid bilayers in water. The permeability to small molecules was similar. The basic membrane physics worked out. Nobody has found one. Nobody has proven they exist outside the constraints of a computational model. But the fact that the chemistry is even theoretically possible, that the physics doesn't forbid it, that the numbers work out, means that Titan's surface is not just a landscape that mimics Earth. It might be a chemistry set capable of inventing an entirely different kind of biology, one that doesn't need water, one that runs on methane, one that, if it exists, would represent not just a second genesis of life in the universe, but a second genesis using completely different molecular machinery, arriving at complexity from a different starting point, under different rules, in a different solvent. That thought is either thrilling or terrifying, depending on your tolerance for the profound and the alien. It is certainly not dismissible. It is arguably the most important question in all of planetary science. There is another piece of evidence that makes the biology question harder to push aside and file under interesting but inconclusive, and it comes from data that is now 15 years old and still hasn't been adequately explained. In 2010, 2 separate studies using data from the Cassini spacecraft pointed to something anomalous happening in Titan's lower atmosphere. The first study, led by Roger Clark at the United States Geological Survey, found that hydrogen molecules flowing into Titan's atmosphere from the outer solar environment seemed to be disappearing near the surface. They were going down in measurable quantities. They were not coming back up in those same quantities. The flux was unbalanced. The second study, led by Daryl Strobel at Johns Hopkins University, found a puzzling absence of acetylene near the surface. Photochemical models, the standard equations used to predict what compounds should accumulate in Titan's atmosphere, given the known chemistry and the known production rates, predicted that acetylene should be building up at the surface over time. It was not accumulating. Something was consuming it, or preventing it from reaching the surface, in ways the models didn't account for. Before Cassini arrived, the astrobiologist Chris McKay had published a paper laying out what a biosphere on Titan's surface might look like. His proposal, methanogenic life, organisms that breathe hydrogen and eat acetylene as an energy source, producing methane as a metabolic byproduct, the same way that certain anaerobic archaea on Earth produce methane as a waste product of their metabolism. The missing hydrogen and the missing acetylene fit that prediction exactly, not approximately. Exactly. Nobody claimed this was proof of life. Non-biological chemistry could in principle explain both observations independently. Perhaps the acetylene is being absorbed into complex organic material on the surface. Perhaps the hydrogen is being lost to some unanticipated atmospheric process. Titan's complex atmospheric chemistry is not fully understood, and gaps in models don't automatically mean life. But the fact that two independent datasets, measured by different instruments using different methods, independently matched a specific biological prediction made years before the measurements were taken. That is the kind of coincidence that makes careful scientists deeply uncomfortable and deeply motivated to go and look more carefully. It is the kind of coincidence that justifies spending several $billion on a rotorcraft mission to a moon orbiting Saturn. What makes it worse, or better, depending on your perspective, is the silence. Titan has all this complexity, all this activity, rain and rivers and seas and weather and underground oceans and missing molecules and theoretical membranes and ancient dunes pointed in the wrong direction. And we have almost no data from the surface. Huygens lasted 72 minutes after landing. One photograph. A handful of atmospheric measurements taken during descent. One brief chemical reading of the surface, a surface temperature, a pressure reading. Everything else we know about Titan comes from orbit, from radar and infrared mapping and gravitational measurements made by Cassini during hundreds of flybys over 13 years. We mapped Titan the way you would map a city by flying over it at night with a flashlight pointed out the window from altitude. You would see shapes in the darkness below. You would infer materials from how the light reflected off different surfaces. You would model the processes that might have created the patterns you observed. But you would not have walked the streets. You would not have smelled the air. You would not have put your hand in the river or picked up one of those ice pebbles and felt how cold and smooth it was. We have touched the ground of Titan exactly once, in one spot, for barely more than an hour. And in that one spot, we found river rocks that weren't made of rock, soil that wasn't made of minerals, and a sky that was a ceiling of smog we couldn't see through. And then the batteries died, and the silence returned, and Titan kept its secrets. NASA is going back. A mission called Dragonfly, a nuclear-powered rotorcraft, something between a helicopter and a planetary rover, heavier and more capable than Mars' Ingenuity by an order of magnitude, is currently scheduled to launch in 2028 and arrive at Titan in the mid-2030s. It will not sit in one place and wait for the wind to bring data to it, the way Huygens did and the way early rover concepts for Titan proposed. It will fly. Titan's thick atmosphere and low gravity create perhaps the most favorable conditions for powered flight found anywhere in the outer solar system. The atmosphere is dense enough to generate lift efficiently. The gravity is low enough that rotors don't have to work as hard as they would on Earth. For a rotorcraft, Titan is almost cooperative, a strange exception in a solar system full of places that resist exploration at every step. Dragonfly will make short hops across the equatorial dune fields, each jump covering about 8 kilometers, gradually working its way toward a target called Selk Crater. an impact site where scientists believe that the heat of the impact collision briefly liquefied subsurface water ice, bringing it to the surface and mixing it with the organic rich sediment sitting on top. That mixing zone, liquid water and organic tholins, even briefly at the same location, is one of the most chemically interesting spots we know of in the entire solar system outside of Earth itself. It is a place where the basic ingredients for water-based chemistry and methane-based chemistry may have briefly coexisted, and whatever reactions happened, there may still be preserved in the crater sediment, frozen in place by Titan's cold, waiting for an instrument sensitive enough to read them. The engineering of Dragonfly alone is a kind of quiet madness, the sort of problem that makes aerospace engineers stare at their whiteboards for extended periods of time and then reach for more coffee. The rotors have to generate lift in an atmosphere 4 times denser than Earth's at sea level, which actually helps compared to, for example, the thin air of Mars, where the Ingenuity helicopter had to spin its carbon fiber blades at nearly 2,500 revolutions per minute just to lift its 1.8 kilogram frame off the ground. On Titan, the atmospheric density works in your favor. What doesn't work in your favor is the temperature. At -179 degrees Celsius, lubricants change viscosity in ways that can seize mechanical systems. Bearings and gears behave differently at cryogenic temperatures than they do in any Earth-based test environment. Electronic components rated for cold environments on Earth, components that have been tested down to -150 Celsius or -160 Celsius, may encounter failure modes that only emerge at temperatures beyond their test range. And the failure modes at those extremes are not gradual. They can be sudden. A component that works at -160 can fail completely at -175 without warning in ways that look fine on every checklist right up until it doesn't. The only power source viable at Titan's distance from the Sun is a chunk of decaying plutonium-238, a radioisotope thermoelectric generator that converts the heat of radioactive decay into electricity. Solar panels would be useless. The sunlight is too dim, too scattered by haze, too attenuated by 1.2 billion kilometers of space to power even a modest instrument suite. Dragonfly will fly for roughly 30 minutes at a time, then land, power down non-essential systems, recharge its battery from the RTG over the following days, and wait for the next flight window. During each ground stop, it will extend instruments into the soil, a mass spectrometer and a gamma ray and neutron spectrometer, capable of identifying complex organic compounds and measuring elemental compositions in the surface material. It will build a chemical portrait of Titan's dune fields, one landing site at a time, slowly assembling a picture of what this world is made of and how it got that way. And it will navigate using maps drawn by Cassini, a spacecraft that was deliberately crashed into Saturn's atmosphere on September 15th, 2017, because its fuel was nearly exhausted after 20 years of operation, and controllers wanted to prevent any chance of contaminating the ocean moons Titan and Enceladus with Earth microbes in an uncontrolled crash decades in the future. Cassini was destroyed on purpose, with full awareness, with a send-off that was part scientific observation and part quiet eulogy. The spacecraft that gave us everything we know about Titan's landscape in detail, the coastlines, the dune fields, the methane seas, the subsurface ocean, the atmospheric chemistry, burned up in Saturn's clouds 2 decades before the mission it made possible arrives at the destination. Dragonfly is navigating with a map drawn by a ghost, following a path laid out by orbital data that is, by the time it arrives in the mid-2030s, approaching 20 years old. The resolution of that map, good as it is, will be challenged immediately by terrain features smaller than Cassini could resolve from orbit. Every landing site Dragonfly selects will be, at some level, a descent into the partially unknown. What Dragonfly finds at Selk Crater could redefine what we believe about the requirements for life, and that is not hyperbole. If the mass spectrometer finds complex organic molecules in that crater, showing signs of structure and organization beyond what random photochemistry would produce, amino acid precursors arranged in non-random ways, or evidence of catalytic chemistry, or molecular structures that appear to be copies of each other in ways that random synthesis wouldn't explain. It would not necessarily mean that Dragonfly found life, but it would mean it found a second example, a second independent location in the universe, where chemistry appeared to be organizing itself in the direction of biology. A second place where the transition from inanimate chemistry to structured molecular complexity had at least begun. And in science, one example is a curiosity. Two examples is a pattern that forces a complete rethinking of the question from how did life begin on Earth to is there something about certain chemistries and certain environments that inevitably tends toward organized complexity, regardless of the solvent? That is a fundamentally different question, and it has fundamentally different implications for what we think we are and where we think we came from, and whether the universe is mostly empty or mostly alive in ways we haven't learned to detect yet. And here's the thing about all of this that deserves more attention than it gets in most discussions about Titan's potential. The question is not just whether life could exist there. The question is what the existence of life on Titan, surface life in methane, or subsurface life in water, would tell us about the distribution of life in the universe as a whole. If life arose on Earth independently, and life also arose on Titan independently, in a completely different solvent, using completely different chemistry, under completely different conditions, then life is not a fluke. Life is what chemistry does when you give it enough time and the right environmental gradients. It is what complexity does when you leave it alone long enough. And if that is true of our single solar system, if the same star's gravitational field contains two independent experiments in the origin of life, one based on water and one based on methane, then the universe, with its hundreds of billions of galaxies and its hundreds of billions of stars in each galaxy, is not mostly empty. It is crowded in ways we have never allowed ourselves to fully imagine. Titan is not just a moon. It is a potential data point in the most important statistical question in the history of science. Are we alone? And every data point we collect from that orange-skied, methane-rained, ice-floored world brings us closer to an answer that will change everything else. Until then, Titan waits. It keeps raining methane into dark rivers that empty into seas no human eye has ever directly observed. It keeps hiding an ocean of water beneath 100 kilometers of ice. It keeps producing organic chemistry in its upper atmosphere and snowing the products down onto dune fields that point in the wrong direction, building up layers of complex molecules that have been accumulating since before the first single-celled organisms appeared on Earth. It keeps wearing Earth's face over a body made of cold and poison and strangeness. Every other terrifying place in the solar system has the decency to look hostile. Venus announces itself as a furnace wrapped in sulfuric acid clouds the moment you look at it, a surface hot enough to melt lead, an atmospheric pressure 90 times what you feel at sea level on Earth, a sky the color of a forge. Jupiter is a wall of radiation and crushing pressure, its radiation belts capable of delivering a lethal dose to an unprotected human in a matter of minutes. Mars is clearly barren, clearly cold, clearly marked by impact craters and dust, and the absence of anything blue or green or living. They show you what they are. They don't pretend to be something else. Titan doesn't do that. Titan looks like a place you could land, a place you could walk, a place with shores and weather and seasons and coastlines that look like home. It invites you in. It borrows the vocabulary of the familiar and applies it to something completely different, and the difference only reveals itself slowly, in detail, when you look closely enough to see what the words are actually describing. The rivers are methane. The rain is methane. The sand is toxin. The pebbles are ice. The sky is smog. The warmth is absent. Every familiar word has an alien definition, and the definitions only matter when you're already standing there. That's what makes it the most disorienting moon in the solar system. Not the cold alone, not the methane alone, not the toxic haze or the hidden ocean, or the alien chemistry or the dunes pointed the wrong way, or the missing acetylene or the theoretical membranes floating in cryogenic hydrocarbon seas. It's the resemblance. It's the fact that Titan studied Earth's homework, copied the format perfectly, the drainage patterns, the coastline shapes, the rain cycles, the atmospheric chemistry, the seasonal rhythms, the dune fields, the river deltas, and filled in every single answer with something from a completely different language. We look at Titan and see ourselves reflected back, and the reflection is off, just slightly, in ways that take time to notice and longer to understand. A world that feels familiar but isn't. A mirror that doesn't quite match. A photograph that looks like home until you read the caption and realize it was taken on a moon where no human has ever stood, in an atmosphere no human could breathe, beside a river no human could swim in, under a sky no human has ever seen with their own eyes. Everything recognizable about it is wrong, in a way that's hard to articulate until you've sat with it long enough, and then it's hard to stop thinking about. If that doesn't unsettle you, spend a minute looking at Huygens's single-surface photograph. River rocks, a flat horizon, orange haze in the background. It could be anywhere on Earth. A dry stream bed in the American Southwest. A gravel plain in Iceland. A quiet, unremarkable stretch of somewhere ordinary that you might walk past without a second thought. It is nowhere on Earth. It is 1 billion kilometers away, on the surface of a moon where rain is made of methane, and the pebbles are carved from water ice, and the air cannot be breathed, and the temperature would kill a human being in seconds without a perfect, untested, chemically resistant pressure suit, and where the ground beneath your feet is wet with liquid hydrocarbons that seep up from sediment layers millions of years deep. That photograph was taken once, in one place, by a probe that died 72 minutes after landing. It has not been repeated. Nobody has been back. Nothing has touched that surface since January 14th, 2005, when a small European spacecraft settled into the methane-wet soil of a moon orbiting Saturn and sent home one picture before the cold and the distance took it. And in the mid-2030s, a small rotorcraft powered by decaying plutonium is going to fly through that orange haze, hop from dune to dune, drop its instruments into the soil at Selk Crater, and tell us what Titan has been hiding under that borrowed face for 4.5 billion years. Whatever it finds, the answer will be extraordinary. Because Titan doesn't do ordinary, it does familiar, and familiar is so much more unsettling than strange. I hope you enjoyed the video, and if you did, please hit the like button. It genuinely helps more people find this channel and keeps these deep dives coming. And if you want to be here when Dragonfly finally touches down and starts answering the questions Huygens left open in 2005, subscribe and hit the bell so you don't miss it. I'll see you in the next one.